All righty. Welcome back from spring break, guys. As people start filtering in here, we're going to go ahead and get started. Today is indeed a busy day. The link has only been up for about 30 seconds now, so I'm going to hold off on diving right in for a few seconds. There we go. Looks like folks are starting to show up. All right, welcome back, lads and ladies. I hope you all had a lovely spring break. I have seen that a bunch of people requested extensions on the spring break homework, which is a little bit disheartening. So if you haven't gotten that done, you need to grind on it, and you need to grind on it immediately, not for the grade, mind you, but for comprehension. So it's very, very important that you understand the content of that homework as we move forwards. That was the idea of having all that extra time to work on it. So I do hope that those of you who made judicious use of the spring break time to study infinite series are coming to a place where you're understanding a little bit what they are about, because they're complicated animals. It really is a slightly challenging subject. But today we're going to move forwards because we must. So this is a lecture. It's the 16th of March. And today we're going to move into section 11.3, which is on the integral test. Which is our second formal convergence test for infinite series. So we've learned a little bit about infinite series so far. We know what the definition of an infinite series is. It's the limit of its partial sum. We know what it means for an infinite series to converge. It means that the sequence of partial sums is a convergent sequence. And we have our test for obvious divergence. That said that if the limit of the ANs, as n goes to infinity, is not 0, then the series sigma AN automatically diverges. But today we're going to start growing our list of convergence tests with this one, the integral test, which we hinted at a little bit on the Thursday before break. So I don't want to hesitate. Let's get into it. Theorem. If AN is equal to f of n, where f of x is a continuous, positive, and decreasing function, then the integral from a to infinity f of x dx converges or diverges together with the series sigma n from a to infinity an. This is the integral test. That's the name of this theorem. So it tells you under certain conditions, your series does the same thing as a type 1 improper integral. That's the idea. Under the right conditions, a series does the same thing as the corresponding type 1 improper integral. And we've looked at this a little bit in the past, actually. When we talked about the harmonic series last Thursday, we actually compared that series to an integral to get us an idea of why that series might diverge. So let me kind of remind you the picture that goes along with this. So, here would be like 1, 2, 3, 4, and so on. And if I have a series whose terms are like A1, A2, A3, and so on, and I kind of form these what look like Riemann rectangles. So the height here would be A4, the height here would be A3, the height here would be A2, the height here would be A1. And you have this pattern continuing. So then the area of this first guy would be A1. The area of the second guy would be A2. The area of the third guy would be A3. The area of this guy would be A4. The area of this guy would be A5. Then you can sort of picture if you have some curve that connects these dots nicely, then the area under the curve, when we think of it like this, is actually bigger than the area of the rectangles. So if the area under the curve is finite, then the area of the rectangles is finite. And if you shift things a little bit, best to redraw this picture, but I'm going to look at what would now correspond to like a left-hand Riemann sum with delta x equal to 1, rather than a right-hand Riemann sum with delta x equal to 1, which is really what we're looking at up there. So now again here, this first height, this would be A1, but I'm going to draw my rectangle going over to the left. Second height would be A2, and I'm going to draw my rectangle going over like this. Oh shit, fuck, god damn it. Here, yeah, sorry. And then my third guy, height A3, with the endpoint on the left. My height here, A4, with the endpoint on the left. And my height here, A5, with the endpoint on the left. This time, if you draw in the curve, it looks like the sum is larger than the integral. The big idea is that the difference between the two is finite. So one will be infinite if and only if the other is infinite. One will be finite if and only if the other is finite. Right? So the curve here is f of x. That's the pencil. And the rectangles represent the terms of the series. So here, imagine the integral of f of x is finite. If the integral of f of x from 1 to infinity is finite, that means that all the area here underneath the pencil curve on and on and on forever is finite. So if the integral in this case from 1 to infinity of f of x dx is finite, then you can see that the sum n from 1 to infinity of an is also finite. Right? The only difference here is that this first block isn't counted. But this first block, of course, this first block has finite area. It's just got width 1 and some finite height. So if the shaded gray area here is finite, that means the integral converges, then all of the area of the purple boxes has to be finite. So if the integral is finite, so is the series. In other words, if the integral converges, so does the series. On the other hand, if you look over here at the sort of left-hand Riemann sum picture, and imagine that the integral diverges, if the integral from 1 to infinity of f of x dx is infinite, well, now these boxes poke up above the curve. So their area is larger than the gray shaded area. Then sigma n from 1 to infinity an is also infinite. So this is the idea, right? If the integral is finite, the series is finite. If the integral is infinite, the series is infinite. And the way to kind of get each one is by thinking about left-hand Riemann sums versus right-hand Riemann sums. Yeah, up here I'm talking about a right-hand Riemann sum for this. So I'm thinking of sigma an as being a right-hand Riemann sum for this integral with delta x equal to 1. And from that perspective, thinking about it in that way, we see that if the integral converges, then the series must converge because the integral is measuring a larger area than the series. On the other hand, if we think about left-hand Riemann sums, again, we think of the integral as measuring an area and the series as measuring an area. The integral measures the gray area, the series measures the area of all the purple boxes. Then if the integral is infinite, since the series here is actually bigger than the integral, if the integral is infinite, then the series has to also be infinite. What this means is that they have to do the same thing. If one is finite, the other is finite. If one is infinite, the other is infinite. There's kind of 4 total things that you could say. If the integral is finite, then the series is finite. And if the series is finite, then the integral is finite. If the integral is infinite, then the series is infinite. And if the series is infinite, the integral is infinite. They play the same. That's the way to remember it.
Does the inverse also hold true?
What do you mean by inverse?
If the series is finite, then the integral is also finite?
Yes, it does. Yep.
All right.
Yeah, so kind of thinking about assuming one of these to converge or diverge in either picture will show you that the other one must do the same. If you assume that the series is finite and think about this picture, then you can see that the integral must be finite because the integral is smaller than the series. Yeah, so what you said is correct. If the series is finite, the integral is also finite. But we use it in the other direction because integrals are easier to compute, right? We learned how to do integrals, type 1 improper integrals. Integrals like this, we learned how to do back in section 7.8. But right now we're trying to wrap our head around infinite series like these. So we think of the integral as being easier than the series. So if you're trying to figure out what a series does, look at the corresponding integral, solve that integral, and then you can deduce that your series must do the same. But there's a big catch here. Under the right conditions. So what are the right conditions? Well, all this shit has to be positive. Can't have anything below the horizontal axis. The other big catch is that the function f of x needs to be monotone decreasing. Shit don't work if this function f of x is allowed to jump up between here and here, right? Imagine that this integral f of x is the f of x function is allowed to turn around and go up to a big peak here before coming down. and then turn around and go to a big peak here before coming down, and turn around and go to a big peak here before coming down, then I don't have any guarantee that the integral being finite, or then I don't have any guarantee that the two are connected to each other in an obvious way, right? Because this picture wouldn't work. If the function is allowed to turn up and come back down here, then the area measured by the integral could be larger, significantly larger than the area measured by the series. So what do we mean by right conditions? Well, that's the hypotheses of this theorem, right? F of x has to be, so what do we mean by right conditions exactly? Continuous, positive, decreasing. You need the function f of x to satisfy those three things. So before you start using this theorem, you need to check that the function that corresponds to your sequence, an, is a continuous positive decreasing function. Then you can say that the series sigma an does the same thing as the integral of f of x. So let's do it. Let's look at an example or two. One of these we've already done, and it's the classic example, the harmonic series. Right, you may remember from Thursday's class, two Thursdays ago, I should say, before spring break, Thursday before spring break, we showed that the series from 1 to infinity of 1 over n is divergent. We were able to do this by like grouping terms. But the really nice way to do this is with the integral test. So here's what we do. We tell our reader, I'm using the integral test. Always do this, right? Always tell me what test you're using. Then identify the function. An equals 1 over n is f of n, where f of x is 1 over x. So my function here, f of x, is 1 over x. Then we have to check. Is this continuous? I should say is, so check. F of x is the following: continuous, positive, and decreasing. Now we should pay attention. I'm summing from 1 to infinity. So I'm checking these things on the interval 1 to infinity. And it turns out you can even relax that a little bit further. If the function isn't positive everywhere here or decreasing everywhere here, as long as it happens eventually and stays that way from some point on, we're okay. But we got to check these. So continuity, yeah, 1 over x, f of x equals 1 over x is a rational function. Which implies that it's continuous except at x equals 0. And 0 is not in the interval 1 to infinity. So remember, rational functions are continuous everywhere except where their bottom is 0. Is this function positive? Well, yeah, f of x equals 1 over x is greater than 0 if and only if x itself is greater than 0. So again, as long as if x is coming from this interval 1 to infinity, then f of x is positive. So yep, we're continuous. Yep, we're positive. Are we decreasing? A few ways to do this. Easiest one, what's f primed? F primed of x here is the derivative of 1 over x, which is negative 1 over x squared. And this is negative for all x except for 0. And that means that the original function f of x is decreasing for all x except 0. All right, so if your derivative is negative, then you are decreasing. So yes, this function is continuous, positive, and decreasing everywhere on the interval 1 to infinity. So those conditions are met. We always check this first when we use the integral test. If any one of these things isn't true, then you stop and you say, fuck, the integral test ain't gonna work. Now we compute the integral. Integral from 1 to infinity, 1 over x dx. Remember how to do this. You need to treat your improper integrals with care. This is the limit as cap r goes to infinity, integral 1 to r, 1 over x dx, which is the limit cap r goes to infinity of the natural log of the absolute value of x evaluated from 1 to r. Which is equal to dot, 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 2. Then cap r to infinity. The natural log of r is going to positive infinity, minus the natural log of 1. Natural log of 1, of course, is 0. And as r goes to infinity, ln r also goes to infinity. So the integral 1 to infinity, 1 over x dx diverges. Thus, by the integral test, sigma n from 1 to infinity, 1 over n diverges also. And that's how these arguments usually look. So take a second, make sure your notes are nice and clear, and then let's see if we have any questions you'd like to ask about this process. Once we're comfy with this, I'll move on to more complicated examples. Again, here, the big idea is that the infinite series is very hard to work with. But the type 1 improper integral is easier to work with. We know how to handle integrals. So instead of messing around with the series, we have this theorem that connects series to integrals. And then when you want to know about the series, you work with the integral instead. But it only works if the corresponding function is continuous, positive, and decreasing. Questions on this? Okay, so there's a whole family of problems that can be solved this way, kind of all at once, and they're pretty important.
Professor, could you show the page 1 second?
Ooh, yeah, okay, here we go. I'll leave it here just for a minute.
Thank you.
All right, we're gonna move on now. There's a large family of problems we can solve all at once using this theorem. You guys remember P integrals? Well, the corresponding family of infinite series are called P series. No, I have not fed her yet, or him. I have not fed him yet. So series of the form sigma n from wherever. I'm going to say from 1 to infinity, but it could start at 2 or 3 or 4. Series of the form sigma n from wherever to infinity, 1 over n to the p are called P series. These converge if P is strictly bigger than 1 and diverge if P is less than or equal to 1. This is an important result that you need to remember, kind of like, our result on geometric series, right? Here's this like whole family of infinite series that we know exactly when they converge. Here's another whole family of infinite series that we know exactly when they converge. Why? Well, we can relate them back to P integrals. Use the integral test. And our previous theorem on P integrals. Right? This is like the series version of a P integral. That's why we call it a P series. So the integral test, here the corresponding function f of x would be 1 over x to the p. This certainly is 1 positive, as long as x is positive, 2 continuous, as long as x is non-zero, and 3 decreasing, because x to the p is increasing on the interval 0 to infinity, its reciprocal 1 over x to the p must be decreasing. This is another nice trick, right? So one of the things you guys are going to be finding is with the integral test, most of your time actually goes into showing that these things are positive, continuous, and decreasing. That's where the majority of the time is spent. And it's nice to have tricks that help speed this up. One of the neat tricks here is that the reciprocal of an increasing function is automatically decreasing. X to the p, that's a power function, right? And here p is assumed to be positive. So certainly x to the p is increasing on the interval 0 to infinity, so its reciprocal would be decreasing. If you want to go through a derivative argument, you can do that too. The derivative of this guy, you could say f primed of x is negative p over x to the, what's that? So negative p times x to the negative p minus 1. which is negative p over x to the p plus 1, is negative for any x greater than 0. Hence, f of x is decreasing for any x greater than 0. These are the two kind of standard arguments to show that a function is decreasing. Either it's the reciprocal of an increasing function, or you show that its derivative is negative. Either one is fine. Therefore, sigma n from 1 to infinity, 1 over n to the p, converges or diverges together with integral 1 to infinity, 1 over x to the p dx. And we know that integral 1 to infinity, 1 over x to the p dx converges if p is greater than 1 and diverges if p is less than or equal to 1. Thus, sigma n from 1 to infinity, 1 over n to the p must do the same by the integral test. And that completes the proof. So our previous theorem on p integrals, remember, Our previous theorem on p integrals was precisely this, that the integral from 1 to infinity, 1 over x to the p dx converges if p is bigger than 1 and diverges if p is less than or equal to 1. That's what we proved about p integrals back in 7.8. And what we're doing now is using the integral test to connect integrals like these to series like these. So p-series form a useful basis for comparison. And we're going to be talking about the comparison tests on Thursday, the first comparison test at least. P-series and geometric series together form a very useful kind of basis for comparison. They're kind of standard fundamental series against which we will compare more complicated ones. And one of the nice things about the integral test is that it lets us prove exactly when p-series converge. So let's real quick look at an example or two. I can hold here for a second, those who are still writing. 10 or something. Sorry about the sniffles, by the way. I should maybe turn on the air to try and filter out some of this pollen. And, how are you doing? Besides handsome, of course you're handsome. How's Lucy doing? He's definitely just opening up. I'm sure he'll come. All righty, does anybody need more time to write? Okay, so some simple examples first. Silly question. Does sigma n from 1 to infinity 1 over n squared converge or diverge? Help me out.
Convergence.
Should converge, right?
Yes. Yeah, why should it converge?
Because it's decreasing, continuous, and positive, so you can relate it to 1x over 2, which is convergent.
That's true. Can anybody say it more concisely, though, without an explicit appeal to the integral test using the theorem we just proved? So you're not wrong, Ethan, you're correct. We could relate this to the p integral 1 over x squared using the integral test because the corresponding function is positive, continuous, and decreasing. But in terms of the theorem we just proved. Yeah, thank you, Matthew. This series converges because it is a p series with p equal to 2, which is bigger than 1. That's it. That's all you got to say. Because this thing is a p series, right? And the theorem we just proved says that p series converge if and only if p is bigger than 1. Right? So kind of the part that we use is everything before the proof, right? The theorem is actually what we're using. So series of this form are called p series. They converge if p is bigger than 1 and diverge if p is less than or equal to 1. So is this series of this form? Yeah, it is. It certainly is. If you take this and plug in p equals 2, you definitely get this. So this is a p series with p equal to 2. And since that's bigger than 1, the series is known to converge. And that's all you got to say. It's easy, right? That's what's so nice about this theorem. All right. How about this guy? Sigma n from 1 to infinity, 1 over the cube root of n. Does that guy converge or diverge?
Diverge because p is equal to 1/3.
Beautiful. Sigma n from 1 to infinity. And remember, I'm writing all these things out like this because I want you guys to mimic the way I'm writing when you write your own solutions. It's a valuable thing to take the time to write out all this stuff. This is equal to sigma n from 1 to infinity, 1 over n to the 1/3. This is a p series with p equal to 1/3, which is less than or equal to 1. Thus, this series diverges. Okay, how about a little bit more? Sigma n from 1 to infinity, e over n to the pi. This looks a little bit fucky, doesn't it?
We take the E out.
Good. E is a constant. This is sigma n from 1 to infinity, e times 1 over n to the pi. First, we kind of realize this algebra is possible. And then e being a constant, he can come out of the series. Remember, this was one of our rules for the algebra of series. So you have e times sigma n from 1 to infinity, 1 over n to the pi. This is not a p series. It's a multiple of a p series. And it might seem like a stupid thing, but the subtle things matter. The devil is in the details. So this is a multiple of a p series. And in this case, what is p equal to?
Pi.
Pi.
Pi. Does the series converge or diverge?
It converges.
Good, because pi is about 3.1415, blah, blah, blah. It's definitely bigger than 1. So this is a convergent series. All right, simple examples so far, some with a little bit weird numbers. I would like to ratchet up the difficulty a bit, but first I want to take a look at, okay, chat, yeah, thank you, Matthew, those are correct. Where do we want
What
to
do you mean it's a multiple of a P series?
Well, I mean, like this piece right here is a P series, and this is the constant multiplying it. So a multiple of something is just, like I say, 10 is a multiple of 2, because 10 is 2 times 5. So this series, my original series, is a multiple of this series, because it's equal to this series times E. If you are equal to a constant times Joe, then you are a multiple of Joe. Does that make sense?
Yeah, so will it change whether it's a convergent or divergent?
Not as long as the multiple is constant, right? And that's why it's a subtle thing. If we want to be really careful here, I should say constant multiple of a P series. Because if this wasn't a constant, it couldn't come out. And if this was a non-constant thing multiplying my series, and whatever that non-constant thing were, if that were to behave badly, then maybe it could change things. But no, if a multiple of a convergent series is convergent, this was actually a part of a theorem we discussed last Thursday. I know it's, sorry, 2 Thursdays ago. It's been some time. So let me jog your memory. Remember this guy? If these are convergent series, then so are these, where C is constant, and these. And in particular, you can pop the constant out. So it's important that you have a constant here, but you can pop constants out, and the result of a constant multiple of a convergent series is another convergent series. All right, let's fiddle a little more. Same thing, but this time, do-
We can see.
oh, sorry, thank you. Let's look at this. This is surely not a P series, nor is it a multiple of a P series. Right, up here, we had a constant and a P series. Down here, though, I can't, there's nothing I can factor out. And even if I could, like, you can't factor an N out of the series because it's not a constant. Constants pop out, but non-constant things don't. So what can I do here?
Split it up.
Very good, Ethan. Very good. Yes, we can do some algebra within my series and write this as root n over n squared plus 2 over n squared. And that will allow me, let me continue over here, say, okay, well, whatever this is, it should be sigma n from 1 to infinity root n over n squared plus sigma n from 1 to infinity 2 over n squared, right? Remember, sigma an plus bn is sigma an plus sigma bn. And now each of these I can clean up a little bit. Kind of use the same brain you use when you integrate. If I asked you to integrate this piece to find an antiderivative for this piece, what would you do?
Could you divide out a little bit of the top from the bottom?
Yeah, these are both powers of n. This is n to the 1/2 divided by n to the 2. So the rule there is that when you divide like bases, you subtract the powers. So I can write there's more n downstairs than there is upstairs, right? N squared downstairs, n to the 1/2 upstairs. That leaves me with 1 over n to the 1.5 or 3/2. And then in the second guy, I can pop out the 2 plus 2 times sigma n from 1 to infinity, 1 over n squared. This first piece like the previous problem is a multiple of a p series with p equal to 2, which is bigger than 1. So this piece is convergent. This piece is just a straight up p series. This is a p series with p equal to 3/2. So what's up with him?
He'll converge because it's more than 1.
Good. 3/2 is 1.5. This is bigger than 1. So this piece converges also. Look, this piece is also convergent. All right, if I add 2 convergent series to one another, what do I get?
You get
Convergent as well.
convergence.
Good. Because it is the sum of 2 convergent series. Right? So if you add finite thing because this converges, to finite thing, this is finite because it converges. You put 2 convergent series together, you get a convergent series. So this guy, which is the sum of this convergent series and this convergent series, must itself be convergent. These sort of arguments are very common, where you take a complicated looking series and you split it apart into 2 simpler looking series. And then you apply separate arguments to each of those 2 simple pieces. And then you make a final argument saying, okay, since each of those pieces do blah, 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 this piece has to do blah, blah, blah. But you need to remember those rules from Thursday before last. So what were those rules? Convergent plus convergent is convergent. What is if I take a convergent series plus a divergent series, what do I get?
The whole thing's divergent.
Good. And what if I add up 2 divergent series? Divergent plus divergent?
Divergent.
Depends, right?
Ah, gotcha. Yeah, this one depends. So if you have the sum of 2 divergent series, it's not immediately obvious that the result is divergent. I'll give you a hint here. If you take 2 divergent series where all the terms in both are positive, that will have to be a divergent sum. But if you have 2 divergent series and you glue them together, it's not automatically divergent. And remember the example we had was like sigma 1 over n and sigma negative 1 over n. Those both diverge, but when you add them together, all the terms cancel and you get 0. So divergent plus divergent is not always divergent. That's the only thing you got to be a little bit careful about. Questions on these first few examples with P series? All right, let's try something else. While we're in this land, let me see, I think this is where one of these lives. In fact, I know this is where one of these lives. 2. Those are good, but well, actually, no, we're not going to worry about that. All right, we good. So let's just get some more practice with the integral test. So again, I'm going to say investigate the convergence of, and I'll give it a name here. I'm going to call the series S. Giving the series a name makes the writing at the end easier, because instead of actually writing the series every time you have to refer back to it, you can just write the letter S. Instead, I advise you to do the same. Investigate the convergence of sigma n from 1 to infinity. Let's say n times e to the negative n squared. It's not geometric. It's not telescoping. You could try the test for obvious divergence, but it'll pass that too. So I'm going to go to the integral test. It's the only other thing we have so far. The function f of x here is x times e to the negative x squared. And I want to know, is this positive, continuous, and decreasing on the interval 1 to infinity? So is this positive on the interval 1 to infinity? Well, e to some stuff is always positive. Any real number you put in the exponent for e, you'll always get a positive thing. Think of the graph of e to the x. It's always above the x-axis. And x is positive on the interval 1 to infinity. So x times e to the negative x squared, it must be positive. Yeah, just say is positive for all x in the interval 1 to infinity. If it's okay with you guys, I'm going to start using this notation. This symbol right here just means in, or is an element of. It's a useful symbol. Your textbook uses it a lot. I've been avoiding it because I don't want to dump too much notation on you. But you get what I'm saying, right? So e to some stuff is always positive, and x is definitely positive on the interval 1 to infinity. You plug in any x value from 1 to infinity, and this thing will certainly be positive. And if you multiply a positive times a positive, you get a positive. So yeah, this function is positive. Is it continuous? Well, x is continuous on its own because it's a polynomial. E to the negative x squared is a composite of e to the u, and u equals negative x squared. Since negative x squared is continuous and e to the u is continuous, e to the negative x squared is continuous. Depending on how good your Calc 1 class was, you guys may have not seen these arguments before. I know many of my Calc 2 students haven't. So I would like to, in just a second, show you where you can kind of research and remind yourself these arguments. Is everybody ready? Does anyone need a second longer to write what we have so far before I go to the textbook? Okay, here we go. My wife took Calc 1 here at Santa Fe. I love Santa Fe. It's a beautiful place full of beautiful people who love their job and love mathematics, but I'll be goddamned if her Calc 1 teacher didn't skip all of fucking chapter 2. So I don't feel bad if you're not familiar with these sort of arguments, but here's some big shit, right? If f and g are continuous and c is a constant, then the following are also continuous. So you add two continuous functions, the result is continuous. Subtract two continuous functions, the result is continuous. Multiply a continuous function by a constant, the result is continuous. Multiply any two continuous functions, the result is continuous. Divide any two continuous functions, and the result is continuous. It gets better. Polynomials are always continuous everywhere. Rational functions are continuous everywhere the bottom isn't 0, everywhere they're defined. And here is the good shit. Where is it? No, come on, goddammit. We've used that theorem in the past. Here we go. Composites of continuous functions are continuous. Those are the main arguments you're going to use in this section as you get through step 2 of your integral test. So what did we do? We said, okay, my function is a product of x and e to the negative x squared. X is continuous everywhere because it's a polynomial. So this piece is continuous. E to the negative x squared is a composite of two continuous functions. It's negative x squared plugged into e to the u. Since negative x squared is continuous and e to the u is continuous, and we have this theorem that says if you compose two continuous functions, you get a continuous function. E to the negative x squared is continuous. So yeah, in fact, this is continuous everywhere. Continuous at all real numbers. And then here's the 4. Why did I write 4? 3. Decrease. This one, I can't say this is the reciprocal of an increasing function because it's not. It's not. This x out here fucks that up. So we got to use the derivative argument. F prime of x is a product rule derivative. Hope you remember your product rule. Differentiate the first guy, leave the second guy alone. That gives me 1 times e to the negative x squared, plus leave the first guy alone, differentiate the second guy. That'll be e to the negative x squared times negative 2x by the chain rule. And if you factor out an e to the negative x squared, what's left here is 1 minus 2x squared. So the critical numbers come from, this piece is never 0. This piece is 0 twice. From 1 minus 2x squared equals 0, which is equivalent to saying 1 is equal to 2x squared, which is equivalent to saying the square root plus and minus square root of 1/2 is x. So our function goes from increasing to decreasing potentially at 2 numbers, plus and minus the square root of 1/2. I'm only interested in the positive one, but I'm going to do the whole number line here. So we'll do negative square root 1/2, positive square root 1/2. And in each of these regions, my function will either be increasing or decreasing. Just for the record, 1 is over here. Right? The square root of 1/2 is smaller than 1. If we test 0, f prime of 0 is e to the 0 times 1 minus 2 times 0. That's 1. So my function, my derivative is positive in here, which means my function is increasing in here. And then if we test something to the right over here, like f primed of, say, 2, that would be e to the negative 4 times 1 minus 2 times 2 squared. 2 squared is 4, 4 times 2 is 8, 1 minus 8 is negative 7. So this is negative 7 e to the negative 4, which is definitely negative. And at this point, I don't really give a shit what's going on over here. So f of x is decreasing for all x greater than 1, the square root of 1/2. And in particular, on the interval 1 to infinity, right? Because 1 is like right here. So yeah, my function is decreasing everywhere on 1 to infinity. It's in fact decreasing everywhere from the square root of 1/2 to infinity. So I can use the integral test. You see what I mean about this taking longer than the integral? It's not a fast process. Down the road, we're going to kind of, the integral test is going to fall out of favor. We're not going to use it unless we have to, precisely because this shit takes so long. This is the number line for f primed. I don't know if you guys remember this stuff very well from Calc 1 or not, but what we're doing here is I'm finding where f primed is positive and negative. I'm solving the inequality. This thing is less than 0. I find that this region is a part of that solution. So you might want to go back to section increasing, decreasing is here. 4.3. Right, if f prime is positive, then f is increasing. If f prime is negative, then f is decreasing. Remind yourselves how to do this stuff. F prime is negative everywhere to the right of square root 1/2, which means f is decreasing. And that's what we wanted to see. Now we compute integral 1 to infinity x e to the negative x squared dx. This is the limit as r goes to infinity, integral 1 to r x e to the negative x squared dx. How do I do this integral?
Substitution.
Very good, you sub. What do I sub for?
Negative x squared.
Yeah, negative x squared is a good choice. You could also get away with x squared. Du then is negative 2x dx. What else do I need to do?
Divide by -2 and then change your bounds.
Yes, very good. We need to make sure we change our bounds. Excellent, thank you, Matthew. So when my old bounds were x equals 1 and x equals r, when x is equal to 1, u is equal to -1 squared, the negative of 1 squared. I want to be clear about that. This negative is not being squared, right? Only x is being squared. So when x is 1, u is -1. And when x is r, u is -r squared. So my new integral will have ln r to infinity integral -1 to -r squared. The x dx gets soaked up by du. I'll have a -1/2 come out. And then here is just e to the u. So I have e to the u times -1/2 du. Just one of the reasons why our integration skills are so important. I can pop out the -1/2. Can come all the way up past the limit. And I have lim r to infinity, integral -1 to -r² e to the u du. This will be -1/2 lim r to infinity e to the u evaluated from -1 to -r², which is -1/2 lim r to infinity e to the -r² minus e to the -1. So now I need to sort out this limit. Got -1/2 limit r to infinity. Here's the way you do this. Rewrite this as 1 over e to the r² minus 1 over e. And now as r goes to infinity, this is 1/2 times 1 over e to the infinity squared minus 1 over e. Infinity squared is infinity, e to the infinity is infinity, so this is -1/2 times 1 over infinity minus 1 over e. 1 over infinity is 0, so this is positive 2 over e. Therefore, what is true? Let's go one thing at a time. Pretend like we're working just from here, like this had nothing to do with anything else. What have we shown in the blue highlighted space here?
Integral has it converges.
Very good. Plus the integral 1 to infinity x e to the -x² dx converges. We can even say what it converges to. It converges to the value of 2 over e. Therefore, what can we say? So now we're coming back and thinking about the rest of the problem as a whole. If this integral converges, what else must be true?
The series converges to 2 over e.
I'm glad you said that. So therefore, the series converges. That's correct. But I want to emphasize this. Not necessarily to 2 over e. So I'm really glad you said that. It's a perfectly reasonable thing to think. But look here. Is the area under the curve the same as the area under the rectangles? No, there's all sorts of shit in the rectangles that isn't involved in the curve, right? So the value of the integral and the value of the series are not the same. They are finite together or infinite together. If one is finite, then so must be the other, but their values aren't necessarily the same. So it's true that since the integral converges, the series converges, but we don't know the value of this series. The term for the value of the series is its sum. But it's probably close to 2 over e. That's a reasonable statement. And in fact, if you want to, your book tells you how to get quantitative about this, meaning it'll tell you like how far off the series can be from the integral. It's always a finite amount, but how far off can it be? It's not true that these are equal. The kind of big idea, so make this note. So warning. In general, the integral from 1 to infinity f of x dx is not equal to the sum sigma n from 1 to infinity f of n. Even if they converge together in the sense of the integral test. So while you will sometimes be able to get the exact value of this integral, that won't tell you the exact value of this series. And it's precisely that picture that I just showed you that illustrates the difference, right? There's some area under the rectangles that isn't counted in the integral, the area under the curve. They do differ. The idea is that they just differ by a finite amount. In your textbook, and you're not responsible for this, so feel free to tune out for about 20 seconds if you want. In your textbook, there is a discussion of how to estimate series using integrals. It's slightly complicated. Here we are. It says that the difference between the full series and the nth partial sum, which we call the remainder, is no greater than the integral from n to infinity of f of x dx. So if you want to know like how far off am I from the actual value of the sum, you can work with this inequality. So it'll tell you that the integral from n to infinity of f of x dx is greater than your remainder, and the integral from n plus 1 to infinity of f of x is less than or equal to your remainder. And then you can say, okay, well, Sn I can compute. S is what I want, and this I can compute. So the piece I want can be solved for in terms of this relationship. And that gives us a way to approximate approximate the series. So if you want an upper bound for the value of your series, take Sn and add to that the integral from n to infinity of f of x. So you compute your nth partial sum, and then add to that the kind of tail of the improper integral. And that will give you something that's a little bit bigger than your series. And if you want to go the other way, find something a little bit smaller than the actual value of your series, take Sn and add to that the integral from n plus 1 to infinity of f of x dx. And this will give you two numbers, one that's bigger than your series, one that's smaller than your series. So you can get kind of an interval of values that your series could take its value from. But I'm not going to make you guys do this. We will be talking about things like this, estimates for series, but there's only one estimation theorem I'm going to require you to learn, and it will be in section 11.5. I'm not there yet. All right. If you tuned out, tune back in.
Question.
Yeah.
How'd you get 2 over e from that multiplication? I don't know why, I just can't see it. It's kind of bothering me.
No, you're right. I'm stupid. It should be 1 over 2e.
Oh, okay. I was breaking my brain trying to figure
So
that
I
out.
distributed the -1/2 here. This piece is 0. This piece is -1 over e. So when I distribute this, this piece is 0, and this becomes positive, and then 1/2 times 1 over e is 1 over 2e. Yeah, I'm so sorry. 1 over 2e. 1 over 2e. Thank you, thank you. Sorry about that. Oh, there's one other instance here. Yeah. All right. Okay, so this is how the integral test goes. It's not the worst thing in the world. It's nice in a bunch of ways. One, it lets us prove what's going on with p-series. P-series are so important because they're so easy to work with. And it lets us handle a bunch of other problems that would otherwise be quite difficult, like this one. You know, figuring out whether or not this series converges, quite tricky with anything other than the integral test, but the integral test works great. That is all we have time for today. There is a new homework up for you, and I want you guys to get started on that. It's not terribly hard, but it does include things from both 11.3 and 11.4. So the 11.3 stuff, that's what we talked about today. It's the integral test. There are some problems that I wanted to work with you that we haven't had time to work just yet. So I will probably start back here on Thursday with 1 or 2 more integral test problems. They take a long time. But go ahead and dive in, get started on that. It's a good homework set. And when you get to the stuff that talks about the comparison test, you can stop. We'll cover that on Thursday. So don't worry about anything that comes from 11.4 just yet, but please do get in there and start working a little bit on the 11.3 stuff. You remember from our last class before break, we talked about the Euler-Mascheroni constant a little bit, the difference between the nth partial sum of the harmonic series and the nth integral of 1 over x. There's a problem in the book that deals with that, and you can show that this is a convergent thing. So somebody asked me after class, how do we know that that's actually a convergent thing? How do we know that those little areas add up to something finite? There's a problem in the book that will walk you through how to show that. It's not the argument that I'm most familiar with. It's in fact a little bit easier, so you might enjoy it. But that's it. Please get started on that homework. Spend a little bit of time. Make sure you finish up the spring break homework first, though. If you haven't done that, that is hugely important, and it's really, really crucial that you understand 11.2 as we move into the rest of chapter 11. So sink in the time now, please, guys. I promise it'll pay off over the next few weeks. And then next time we're going to talk about how to compare one series to another. And then we're moving on. We're going to have like 5 more convergence tests for infinite series before exam 2. Exam 2 is probably about 2.5 weeks out. But I'll talk to you as we get closer. All right. Take care. Have a wonderful afternoon. And I'll see you guys all on Thursday.
Thank
Have a great day, Professor.
You too. Thanks.